The next chapter is on superposition of waves. In this chapter, you will come across these topics. After completing them, you should be able to explain and use the principle of superposition of waves, explain experiments that show diffraction and interference, solve problems involving two slit and multiple slit interference. Okay, so let's first have a look at the whole chapter so that you can have an idea. You have to memorize the principle of superposition with understanding, because in the exam papers, especially in paper 2, they can ask you what is the principle of superposition. Okay, so here it's given: when two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. So this is the principle of superposition. Now we will learn more about it. And I have told you before, whatever is highlighted in green like this, whatever is in this green box is very important. You have to memorize the meaning with understanding. And also whatever is in bold letters like this, especially in green bold letters, is very important. You have to memorize the definitions or the meaning with understanding, because in paper 2 they can ask you to write the definition or write the meaning of these things. Okay, then we have diffraction. All waves can be reflected, refracted and diffracted. Okay, then this is some example with the ripple tank. This is called a ripple tank, and so we will see diffraction of water waves, diffraction of electromagnetic waves, for example radio waves, microwaves, interference of waves. Then so here is what happens. We are going to use the principle of superposition to find the displacement of the resultant wave. Okay, we will see interference. Okay, you will learn what is path difference, phase difference. Path difference is given in terms of wavelength. For example, here lambda is one whole wavelength. So if it's 2 lambda, then it's 2 whole wavelengths. So path difference is given in terms of wavelength, lambda. But phase difference is given in terms of angle. For example, radians or degrees. Okay, so here is the interference of this electromagnetic wave. Okay, light wave, to be specific, the laser wave, monochromatic light. So for the interference to occur here, remember the wavelength of the gap, the wavelength of the waves and the size of the gap should be almost the same. If the size of the gap is approximately equal to the wavelength of the waves, then you will have noticeable diffraction. So over here you have to also remember the wavelengths of the waves. Remember in the previous chapter I told you all that you all should know the wavelengths of the electromagnetic waves, for example radio waves, microwaves, visible light, like that. So then you can have an idea of the size of the gaps here should be for interference to occur. Now at the gaps there will be interference, and on the other side, at the gaps there will be diffraction, and on the other side there will be interference. So each slit will cause the wave to diffract. Okay, something like what we saw, I think there was a picture earlier. Yeah, something like this. So the waves are coming like this, and this is there will be, so this is one gap here, this is one gap, this is another gap. So there will be diffraction here and also diffraction here at each gap. Then what happens? The waves that come from the other side, they interfere. Okay, so we will have diffraction, and on the other side we will have interference of the waves. So at the gap, the spreading of the waves is called diffraction. Spreading of a wave at the gap is called diffraction. So when those waves interfere, we have interference. Okay, so so here this is the diffraction, and on the other side we will have interference of microwaves. Now you can't see these waves. Microwave is out of the visible region, so you will not be able to see the microwaves diffracting. That's why we use the microwave probe. So you can't see anything on this side, but you can detect it using the microwave probe. Okay, so here you can see there is one gap here and another gap here. So there will be diffraction at this gap and also diffraction at this gap. So as a result, there will be interference on this side. Okay, and when they interfere, we will learn using the principle of superposition there will be areas where there will be no displacement and areas where there will be maximum displacement. Okay, so we will see those details. Then you also have to know what is coherence, coherent source. Okay, that is also very important. In the exam papers they can ask you. We say that they act as two coherent sources of sound waves. Coherent means sticking together. Now again, this is not a very good explanation. So what you can do is you can see the meaning of this word in the glossary. Then you can have a better understanding of that. Okay. Then again, very important, the Young's double slit experiment. In this experiment, there is an equation that you should know. And that equation is this one right here. You have to know what each symbol here means. See, the meanings are given here and you should be able to identify it from the diagram. So the equation is lambda equals ax over d. Lambda is the wavelength of the waves. So the wavelength of these microwaves. A is the slit separation. Here you have one slit, here you have another slit. Then x is the fringe separation. That means from one bright fringe to the next bright fringe. Now what happens is, due to interference, there will be dark fringes and bright fringes. So this x is the distance between the center of one dark fringe to the center of the next dark fringe, or the center of one bright fringe to the center of the other bright fringe. Remember, it's not the distance between adjacent dark and bright fringes. It is between either from one bright fringe to the next bright fringe, or from one dark fringe to the next dark fringe. Okay, so this equation very important and you should understand this and you should be able to identify it from the diagram. There have been several questions from this in the exam papers. So make sure you really understand this very well. It's very easy. Only thing is you have to know the equation, then what these symbols are and how to use it based on the diagram. So you should be able to identify where is A, where is D. D is the slit to screen distance. This is the slit, this is the screen. The perpendicular distance from the slit to the screen, that is D. So lambda equals x over d. Then there are some questions using that. And then here is another one, something similar to that. Now over here, we can send this light because this is a monochromatic light. But if it's not monochromatic, monochromatic means it is only red light, so only one wavelength. But if it's something like this, we will have to use a filter. So this single slit will give this, and then you will have two doubles, you will have double slit like this. Now here you have interference, you see, where the two regions overlap, that is where you have interference. So the waves are diffracted, and when the diffracted waves overlap, you have interference. Okay, then diffraction grating also very important. Okay, then we will come across diffraction grating, and over here there is another equation, very important equation, that is this one. N lambda equals d sine theta. Again, in the exam papers, I have seen questions where you have to use this equation. So you have to be very familiar with how to use this equation. Okay, so here what is n, what is lambda, what is d, what is theta, all of those are important. Okay, so this theta here is the angle from the central one. Okay, central maximum. So that is from n equals to 0 to n equals 1 or n equals 2 or n equals 3, whatever the n, that is the angle from n equals 0 to that n. Now if you substitute 2 for n here, then the angle will be from here all the way to here, because this is n equal 2. So from here n equals 0 all the way up to here, that is n equals 2, that will be the theta. If you use 1 for n here, then this will be the angle from n equals 0 to n equals 1. Now there can be n equals 1, n equals 2, n equals 3, 5, it depends. Okay, there can be several n values. Here they have shown only n equals 1 and n equals 2. And on the other side it is symmetric. So the angle here and the angle here are the same value. Then again the angle from here to here and the angle from here to here will also be the same value. So this is actually like a line of symmetry. The n equals 0 is like a line of symmetry. Okay, so now you know what is n, you know what is theta. Lambda is the wavelength of the waves. D is the slit separation again, but here you have several slits. It's like a comb. you have like several gaps here, so you have to find D. Now normally in questions they will tell you how many gaps or how many slits are there, and you have to find the distance between adjacent slits using that. Okay, so actually when we go through this example you will understand it. See, for example, over here monochromatic light is incident normally on a diffraction grating having 3000 lines per centimeter. Now in 1 centimeter there are 3000 lines. You have to find the distance between the lines. So that then what do you have to do? 1 centimeter for 3000, then D is equal to 1 divided by 3000, which is this. Okay, so that means from one slit to the next slit, that slit separation is this value. It is also called the grating spacing. See, slit separation, D is also called grating spacing. That's how it, and then you can figure it out after that. See, the angular separation, that is theta. I told you before, from the 0, n equals 0 to n equals 1 or 2, whatever, that is called the angular separation, theta. The angle theta is called angular separation. So here they have given from 0th and 1st. So here in this case n equals 1. When n equals 1, theta equals 10. Can you see that? When n equals 1, theta equals 10. Okay. So this is just an overview. Later on we can do. So again you are using that equation, n lambda equals d sine theta. Okay, so let's quickly go through the summary, because this way you will have good understanding of what you are coming across in this chapter, and it will be easy for you to understand this chapter. Okay, so the principle of superposition states that when two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. Okay, so to help you understand this better, let's have a look at the first topic, which is about the principle of superposition. So what happens is you will have two or more waves coming together, and the resultant of these waves, the resultant displacement of these waves is the sum of the algebraic sum of the displacement of the individual waves at that particular point. So let's go through that. Now there is another nice example here where you will have to find that. Okay, you see here. So you have the green wave and you have the blue wave, blue colored wave, the green colored wave, and you have the red one is the resultant. So what you will have to do is, now this is displacement, this is distance. Can you see? So if you go along this line B, the displacement of B is from here to here. The displacement of wave A along this line is from here to here. You see, that is the displacement. So the displacement of the resultant wave, which is shown in red here, will be this displacement of the green wave, which is from here to here, plus the displacement from here to here. So if this was, let's say, 3 here, and if this was 5 here, then it will be 8 here, because 5 plus 3. And also the sign is important. Okay, here both are positive, so this is, let's say, plus 5, this is plus 3, then this will be plus 8. Okay, but if it's negative, you have to consider the negative sign also. Now you can see over here, maybe this is, we can say here the blue wave here is, let's say, minus 5, and let's say this is plus 6, the green one. So then it will be plus 6 minus 5, which is plus 1. You see that? So here it will be plus 1. Okay, so like that you should be able to figure it out. And there are some more examples here to help you understand it better, and there are questions also. Yeah, so we'll go through a little bit more. Okay, we'll go through another example using the same diagram. If you look at this point here, over here, here for the blue wave it's 0, right? For the green wave maybe it's like plus minus 7 or something. So it's 0 plus minus 7, which is again minus 7. So the resultant wave here will have a displacement of minus 7. Now here both are 0, so the resultant wave also will have 0 displacement. So like that you should be able to understand it. Alright. Okay, so we have the principle of superposition. When two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. Now I think you understand it better. Okay, then we have diffraction. So make sure you answer all these questions in the brown boxes, because that will ensure you have the minimum knowledge required to answer the past paper questions. So in any of these chapters, you have to always answer all the questions in the brown boxes. The questions are based on the theory that was taught. So obviously first you have to understand the theory very well, then you do the questions. So make sure you understand everything in this book. Anything that is not clear should be cleared. Don't have any doubts in any of the pages in the book. Okay, so that what I explained here is the explanation here. Then diffraction. Diffraction is the spreading of a wave as it passes through a gap or around an edge. So it can just be one edge of a gap also. Without it being a gap, it can be even an edge. So around the edge also diffraction can occur. It is easy to observe and investigate diffraction effects using water waves as shown in box 14.1. Okay, then I told you before, all the waves can be reflected, refracted and diffracted. So here we have diffraction of sound and light, but sound waves have a long wavelength compared to light waves. So that's why sound can diffract around large edges. For example, if you are in one room and if the door is open and you are in the kitchen, then you can hear what people are talking in the room, because the sound can diffract around the door edge, because the size of the door gap, the size of the pathway, that is the size of the door, the width of the door gap is approximately equal or around or in the order of the wavelength of sound waves. Remember, we have learned in the O-level class, for diffraction to occur, the size of the gap should be equal or approximately equal to the wavelength of the waves. So in this case we are talking about sound waves now. So the size of the gap, if the gap is in the range of the wavelength of sound waves, then diffraction can occur around that gap. That's why when you are in one room, if the doors are open, you can hear what people talk in the other room. But this is not the case with light. Now in the case of light, you can see the wavelength is about this much. I told you before, when we were learning the previous chapter, you have to know the wavelengths of the waves in the electromagnetic spectrum. Visible light is one part. So visible light, the wavelengths are from 400 to 700 nanometers. So you have to remember those wavelengths. Visible light has much shorter wavelength also. For diffraction to occur, the size of the gap has to be this small. Now that's why if you are in one room, if you point a torch, it can't go all the way around to the other room, because diffraction can occur. Maybe you can get reflection. There can be reflection and you can see the light in the other room, but it can't go all the way around, because diffraction can't occur if the size of the gap is not in this range, around this value. It is not diffracted noticeably by doorways, because the width of the gap is 1,000,000 times larger than the wavelength of light. However, we can observe diffraction of light by passing it through a very narrow slit or small hole. Now, when I showed you this before, when we were going through the Young's double slit experiment and all, we learned that that gap size has to be around this small. Okay, then only diffraction of light waves can occur. So here you can see by passing through a very narrow slit, when laser light is directed onto a slit whose width is comparable to the wavelength of the incident light, it spreads out into a space beyond to form a smear on the screen. Figure 14.5, that is here. See, diffraction, light is diffracted as it passes through a slit. An adjustable slit allows you to see the effect of gradually narrowing the gap. You can see the effect of diffraction for yourself by making a narrow slit with your thumbs and looking through the slit at a distant light source. By gently pressing your thumbs together to narrow the gap between them, you can see the effect of narrowing. The slit. Okay, so about the diffraction of water waves, now you can see this. We can adjust the wavelength of the water waves by adjusting the frequency of vibration of this vibrating bar. Now you can see this vibrating bar will be connected to a signal generator. So from the signal generator, we can get the frequency of vibration that we want, and that will be the frequency of, so let's say we adjust the signal generator to a certain frequency, then this will vibrate at that frequency. So the frequency of the water waves that this vibrating bar produces as a result of the vibration will be the same frequency as the source. So always the frequency of the waves will be the same as the frequency of the source. Not only here, even in other examples. Okay. So if you know the speed of sound in water, then using V equals F lambda, the wave equation which applies to all the waves, you can find the wavelength. Okay, or you can even see it here, from one crest to the next crest, that is one wavelength. And if the size of this gap is equal or approximately equal to the size of the wavelength of these water waves, then you will have noticeable diffraction like this. Okay, so you can see here, this is the gap and diffraction is occurring. Diffraction is the spreading of a wave as it passes through a gap or around an edge. So again, this word here is in green bold letters. That means you have to know the meaning. In paper 2, they can ask you to write down the definition of diffraction. So you have to write this. And you can go through the glossary also for a more detailed meaning. Okay. Then you can see here what happens when you increase the gap width. So if you start with this, there is prominent diffraction. Then what happens when you increase the size of the gap, keeping the wavelength of the waves constant? If you increase this, then the diffraction becomes less and less. Okay, so you can see even less diffraction. So the spreading out is less and less when the size of the gap is much larger or smaller compared to the wavelength of the waves. Okay, then we have diffraction of radio and microwaves. These are also electromagnetic waves. But radio waves and microwaves have the longest wavelengths of the waves in the electromagnetic spectrum. You have to know the wavelengths of the waves in the electromagnetic spectrum as well as in the order also. So the radio waves have the longest wavelengths, then microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. So you have to know them in that order. And also you have to know the wavelength. So remember, radio waves is from 10 centimeters to more than 10,000 meters or more than 10 kilometers. So one wavelength for radio wave can be that large. But microwaves is from 1 millimeter to 10 centimeters. So you have to know these wavelengths. Okay. So in the previous chapter, the wavelengths and all of those details of the electromagnetic spectrum were given. So radio waves can have wavelengths of the order of a kilometer. These waves are easily diffracted by gaps in the hills and tall buildings around our towns and cities. Microwaves used by mobile phone networks have wavelengths about 10 centimeters. These waves are not easily diffracted because their wavelengths are much smaller than the dimensions of the gap and mostly travel through space in straight lines. Cars need external radio aerials because radio waves have wavelengths longer than the size of the windows. So they cannot diffract into the car. Now, if it's to now the wavelength is much greater in the radio wave, so it can't diffract through the window into the car. That's why we have the aerial outside the car, because the size of the gap in the window is small compared to the wavelength of the radio waves. If you try listening to a radio in a train without an external aerial, you will find that FM signals can be picked up weakly. Their wavelength is about 3 meters, but AM signals with longer wavelengths cannot get in at all. Now in the A2 class, A-level class, you will learn, in second year, you will learn FM and AM modulation. FM stands for frequency modulation, AM stands for amplitude modulation. So details are there. There's a chapter called communications. In that you will learn. I have also uploaded the video for that as well. Okay, so make sure you do these examples here. Okay, then explaining diffraction. Diffraction is a wave effect that can be explained by the principle of superposition. We can think about what happens when a plane ripple reaches a barrier in a gap. Now there is a diagram. So these are called plane waves. When they are parallel, when the wave fronts are parallel to each other, those are called plane waves. If they are circular, then those are called circular waves, circular wave fronts. Here we have parallel or plane wave fronts. Reaches a gap in a barrier. Each point on the surface of the water in the gap is moving up and down. So normally the wave fronts represent the crests of the wave. The top of the crest of one wave is like one wave front, and then this is the next crest. So we use another wavefront like this. Each point on the surface of the water in the gap is moving up and down. Each of these points moving points can be thought of as a source of new ripples spreading out into the space beyond the barrier. Okay, so that is when diffraction occurs, it spreads to the other side. Now we have a lot of new ripples, and we can use the principle of superposition to find their resultant effect. Without trying to calculate the effect of an infinite number of ripples, we can say that in some directions the ripples are added together, while in other directions they cancel out. So you can see here, if you take the ripples from this point A, though that is what you get, then from B, so it's just one gap here. Okay, previously I was explaining it, I was like assuming that this is the separation between this gap and this gap, but that is not the case actually in this diagram. But in the previous explanation also what I explained is fine. Okay, so I assume that this here is one gap and this here is another gap, but here it's only one gap, and they are referring to 3 points on the gap A, B and C. So if you see here, it will come like this, then at B it will come like that, and at C it will be like this. So here is the center of that circular arc. Then what will happen? These will interfere, and as a result you will get one big circular wave like that on this side, and that is the result of all this interfering and producing the resultant wave. Ripples from all points across the gap contribute to the pattern in the space beyond. Okay, then we have interference. Okay, interference, adding waves of different wavelengths and amplitudes result in complex waves. We can find some interesting effects if we consider what happens when two waves of the same wavelength overlap at a point. So what happens? Two waves of the same wavelength overlap at a point. Again, we can use the principle of superposition to explain what we observe. Okay, so is here observing interference. Now what happens is both of these are connected to the same signal generator. So that means they will be in phase. That means as soon as this loudspeaker cone moves forward, at the same moment this is also moving forward by the same amount. So what will happen is that is what we call in phase. So as soon as this produces one compression, here also on this side there will be a same compression. So that's why the waves are what we say coherent. Okay, in phase and coherent. So you can get places of you can get quiet places and loud places. Okay, so what is coherent? Two sources are coherent when they emit waves with a constant phase difference. Now we might wonder what is phase difference. Phase difference, scroll down, this is the glossary. Okay, NOP, phase difference. The difference in phase of two oscillating particles expressed in degrees or radians. Okay, so actually there is a better meaning to this coherent and phase difference. Adding waves of different wavelengths and amplitudes, we went through this, I think. Okay, anyway, I'll explain this part again. We can find some interesting effects if we consider what happens when two waves of the same wavelength overlap at a point. Again, we will use the principle of superposition to explain what we observe. So here is interference of sound waves. A simple experiment shows what happens when two sets of sound waves meet. The two loudspeakers are connected to a single signal generator. Figure 14.11. They each produce sound waves of the same wavelength. Now because they are connected to the same source, the waves will be having the same wavelength, frequency, they will be in phase, they will have a constant phase difference. They are coherent, in other words. They each produce the sound waves of the same wavelength. Walk around in the space in front of the loudspeakers, you will hear the resultant effect. That means in some places where the crest of one wave meets the trough of the other, the resultant is 0. If you apply the principle of superposition, let's say the crest of the wave from this meet at the trough of the wave from this, then the resultant displacement is 0. So you will get minimum sound. And if the crest and crest or trough and trough meet, then the amplitude doubles. The displacement will be maximum and it will double, right? So you will get a loud sound. So there will be areas where there is destructive interference, where crest and trough meet, and constructive interference where trough and trough or crest and crest meet. Okay, so we will see this in detail with some diagrams afterwards. The sound waves from two loudspeakers combined to give an interference pattern. This experiment is best done outside so that reflections of sounds or echoes do not affect the results. Because when you do outside, reflections cannot occur. Reflection of sound is called echo, because the echo can come and then it can interfere with those waves. Okay, so here you can see we can do the same thing with the ripple tank. So actually there are some videos online that you can watch what happens with this. So what happens is here, now earlier you had that vibrating bar in the water, now here it's above the water. So what will happen, this will vibrate and you have this, okay, the spherical things. So what happens is when it goes up and down in the water, it will create circular ripples. Okay, now these circular ripples, when the crest of one meets the trough of the other, there will be destructive interference. When the crest and crest or trough and trough meets, there will be constructive interference. So as a result, there will be places along this where the displacement is zero. The water is not moving up or down, okay, because they are vibrating at a constant frequency, and also they are coherent. They have same wavelength, same frequency, okay, and they are in phase. So because of that, you will see that it looks as if it's stationary, okay, because where constructive and destructive interference occurs will be at the same places. Okay, so here is a diagram to help you understand that. Now you can see the blue wave and the green wave are going together here. That means there will be constructive interference. So it's actually two waves here, but because they are going together, you can see it as one. So what will you do? Double the displacements for each. Then you will have the resultant displacement. Similarly, over here you can see, here the displacement is positive, here it is negative. Then what happens? It will be zero. Okay, so if you take this point vertically, if you look at this, here it will be maybe +2, here it's -2. So the result there is 0. So that's why the resultant will be 0. So this is destructive interference. Where the crest and the trough meet, there will be destructive interference. Where trough and trough, or crest and crest, or trough and trough meet, there will be constructive interference. So the amplitude doubles. The resultant wave will have double the amplitude of the waves that interfere to produce that resultant wave. If it's like this, here it will be 0. Now if the waves have different amplitudes or different displacements, then again you can figure it out. For example, here it's 1, here it's 2. So then this is 1 plus 2, then 2 plus 1 is 3. Here it will be 3. Like the way we did the previous example in the beginning, you can do it for this also. Here it will be -1, -2. So -1 minus 2 is -3. So this is adding waves by principle of superposition. Blue and green waves of the same amplitude may give a constructive, here constructive, B destructive interference according to the phase difference between them. Now the phase difference here is 0 degrees because the waves go together, or we can even say 360 degrees. Okay, here it is 180 degrees. Here the path difference is 2 lambda or 0 lambda because both waves go together. Here one wave is lagging behind the other by one wavelength. They have the same wavelength, but one is coming after one wavelength, or after half a wavelength. Sorry, here it can be half a wave. Here it's one. So from here to here, that is one wavelength. Okay, so it's like one whole wavelength apart, 1 or 2 or 0. If it's an whole number of wavelengths that one wave is lagging behind the other, then you get constructive interference. But if it's half a wavelength, 3.5, 2.5, like that, so if it's lagging by half a wavelength, then you will have destructive interference, because if it's half a wavelength away, then the crest and the trough meet, so you get destructive interference. Okay, so according to the phase difference between them, waves of different amplitudes can also interfere constructively. Here the amplitudes of the two waves are different, but they are in phase. They are having a phase difference of n times 360 degrees. Here it is half a wavelength, 2.5, like that. So the crest and the trough meet here. We will see the details afterwards. Actually, there is an equation also. Okay, at other points something different happens. The two waves arrive completely out of phase or anti-phase. Phase difference is 180 degrees. So that means one wave is half behind the other by half a wavelength of 180 degrees. Because for one whole wavelength, that is lambda, we can also say it is 360 degrees. There is cancelling out and the resultant wave has zero amplitude. So that is the diagram B. At this point we could expect silence because this is sound wave. We are talking about this now. But if it's in the case of water waves, then the water doesn't move up or down at that point, because the displacement is zero. At other points, the waves are either perfectly out of step or perfectly in step, and the resultant has amplitude less than that at the loudest. Okay, so for example, at other places like here, where two waves arrive at a point in phase with one another so that they add up, we call this effect constructive interference. Where they cancel out, the effect is known as destructive interference. Where two waves have different amplitudes but are in phase, that is the diagram C, they are in phase but have different amplitudes. Constructive interference results in a wave whose amplitude is the sum of the two individual amplitudes. Okay, so here actually this is for this diagram or this one. This experiment, you can draw the wave fronts like this. And then what we will have is, now the wave fronts represent the top of the crest. So for the waves that are produced by this, that is shown in red. For this yellow one, it is shown in blue. Okay, the waves that is produced by this yellow one, it is shown in blue. Because this moves up and down, it dips in the water and comes out, so it produces circular waves. Then what happens? Now what happens? You can see here, this is the crest. If you look at point B, this is the crest of the red wave, waves from this red one, and you can see B is also the middle of two crests for the blue waves, the waves from this, because between, in the middle, from one crest to the next crest, in the middle you have what? Trough. If you look at a wave, for example, if you like take this wave for example, from one crest to the next crest, in the middle you have a trough. So what will happen if trough and crest meet? There will be destructive interference. So that is what they are actually showing you here. So at B, here we have crest, and here between two blue you have trough for the waves from this. So here what you have, trough and crest are meeting, so there will be destructive interference. Here crest and crest is meeting, so you will have constructive interference. Whether the waves combine constructively or destructively at a point depend on the path difference of the waves from the two sources. The path difference is defined as the extra distance travelled by one of the waves compared with the other. Okay, at point A in figure 14.15, the waves from the red source have travelled three whole wavelengths. Let's check that. So 1, 2, 3 at A. And this one 1, 2, 3, 4 wavelengths. So here what you have, 3 waves and 4 waves come together. So the 3 wavelengths, here exactly 4 wavelengths. So then you will have constructive interference. Okay, so because trough and rough meet. So the path difference is 1 wavelength. The waves from the yellow source have travelled 4 wavelengths. The path difference between the two sets of waves is 1 wavelength, because 4 minus 3. A path difference of 1 wavelength is equivalent to a phase difference of 0 or 360. That's fine. Okay, so remember, path difference is given in terms of wavelength, lambda. So here it's 1 lambda. The path difference is 1 lambda. the phase difference is given in terms of angle, either degrees or radians. This means that they are in phase, yeah, because they are in phase, because it's the exact number of whole number of wavelengths. This means that they are in phase, so they interfere constructively. Now think about the destructive interference at point B. Okay, that is this one I told you here. Again, you can count 1, 2, 3 waves here, 3 wavelengths. Here it is 1, 2.5 wavelengths. So the path difference is 3 minus 2.5, which is half a wavelength. So that means crest and trough are meeting, and you can see it from here. So there will be destructive interference there. At point B, the waves from the red source have traveled 3 wavelengths. The waves from the yellow source have traveled 2.5 wavelengths. The path difference between the two sets of waves is 0.5 wavelengths, which is equivalent to phase difference of 180 degrees. Okay, so again, if you look at this diagram, from here to here, that is one whole wavelength, because from here to here, one whole wave. So from here to here, the middle, from the trough to the crest, or crest to trough, that is half a wavelength, or 180 degrees. Okay, so in that case, the phase difference is 180 degrees. The waves interfere destructively because they are in antiphase. So when crest and trough meet, we say they are in antiphase. In general, so or else we can also say, if it's a half number of wavelengths like this, half, 1.5, like, then you have destructive interference. If it's a whole number of wavelengths, then you have constructive interference. In general, the conditions for constructive interference and destructive interference are outlined below. These conditions apply to all waves: water waves, light waves, microwaves, radio waves, sound waves, etc. that show interference effects. In the equations below, n stands for an integer, any whole number including 0. So remember, for constructive interference, it should be a whole number of wavelengths. Okay, so 0 lambda, path difference I told you is given in terms of wavelength lambda. For destructive interference, the path difference is an odd number of half wavelengths. So remember, odd number of half wavelengths. So it's half lambda, 1.5, 2.5, like that. Path difference, then we can give it like this, because n is a whole number. So if n is 1, then 1.5, you get this. If n is 0, you get half lambda. So the path difference is always, one wave is like a half or 2.5, something like that behind. For destructive interference to occur, one is lagging behind the other by a half number of odd number of half wavelengths. That's how you state it. Then we have interference of light waves. So I went through this briefly previously also. Now this is monochromatic light, laser beam. Then same thing you can do with the microwaves also. Okay, so when you do it with the microwaves, and when you move the microwave probe along, let's say, certain line, then there will be quiet regions, regions where the reading is minimum or 0, and readings where it is maximum. So where it is minimum is where destructive interference takes place, and minimum is where destructive interference takes place, maximum is where constructive interference takes place. Okay, then about coherence, we are surrounded by many types of wave: light, infrared, radiation, radio waves, sound, and so on. There are waves coming at us from all directions. So why do we not observe interference patterns all the time? Why do we need specialized equipment in a lab to observe these effects? In fact, we can see interference of light occurring in everyday life. For example, you may have noticed halos of light around street lamps or moon on a foggy night. You may have noticed light and dark bands of light if you look through the fabric at a bright source of light. These are interference patterns. Now again, like what I said here, because it is coming from the same source and then interfering here, they will be in phase. Now if you use two different sources and try to interfere, it would not work, because they can have different frequencies, different wavelengths. But if it's coming from the same source, they will have the same frequency, same wavelength, constant phase difference. That's why you can have the constructive and destructive interference clearly at certain points, and it will not change, the position will not change. But if you use two different sources, then the waves might come at a different rate in one or slow in other, and it will not be, then we say, coherent. That's why we need coherent sources. Okay, so here it is actually explaining now. We usually need specialized arranged conditions to produce interference effects that we can measure. Think about the demonstration with two loudspeakers. if they were connected to a different signal generator with slightly different frequencies, the sound waves might start off in phase with one another. Okay, so if you use different signal generators like this, if you use two different sources instead of one, without this, then what will happen? You can get diffraction, but what will happen? They will go out of phase after some time. They will not be in phase, in other words. The sound waves might start off in phase with one, but they would get soon out of phase. We would hear loud, then soft, then loud again. The interference pattern would keep shifting around the room. So here it will always be in the same place. But if you use two different sources, then that position where destructive interference occurs can be going from one place to another, because it will be something like this. In the beginning they might come in phase and then they will be out of phase, like I said before. So because it's not coming from the same source, that's why we use the same source. By connecting two loudspeakers to the same signal generator, we can be sure that the sound waves that they produce are constant in phase with one another. We say that they act as two coherent sources of sound waves. Coherent means sticking together. Coherent sources emit waves that have a constant phase difference. Now this is the important thing. Okay, so if waves are coherent, they will have a constant phase difference. Now in the exam they had asked this question. So remember, if it is a coherent source, those waves will be having a constant phase difference. That means they will have the same frequency and they will be in phase. Okay, so here this phase difference, which means it's given in terms of angle. So if the phase difference is constant, obviously the path difference is also constant. It's the same thing, but we are giving it in a different way. Path difference is given in terms of wavelength. Phase difference is given in terms of angle. Note that two waves can only have a constant phase difference if their frequency is the same and remains constant. So this is what we mean by constant phase difference. Again, this was also asked in the exam paper. So constant phase difference means their frequency is the same and remains constant. So coherent means they have a constant phase difference, and constant phase difference means they have the same frequency and it is constant. They have a constant phase, their frequency is the same and remains constant. Okay, so same thing they are explaining with the laser also. Then like I said, the Young's double slit experiment is very important. So where you have the bright fringes is where you see the red dots. Okay, dark fringes is where you have the dark spots. So after every red dot you have a dark spot, and then after every dark spot you have a red spot or bright fringe. Dark spot is called dark fringe or minima, because for there to be a dark fringe there has to be destructive interference. It's like the quiet place. If you use sound waves, now this is microwave. If you use sound waves, there will be regions where the sound is minimum and sound is maximum. Minimum where destructive interference occurs, maximum where constructive interference occurs. Similarly, for the microwave waves, there will be regions where there will be a maximum signal and minimum signal. Maximum signal corresponds to where you have constructive interference, and minimum signal corresponds to where you have destructive interference. Now similarly with the light waves also, now here you can see it's coming from a coherent source, so diffraction occurs at this slit and this slit. This is a double slit, okay, like this, it's a double slit. So diffraction occurs, and then where they interfere there will be, where they overlap there will be interference. So when there is interference you will have constructive interference and destructive interference. If it's constructive you will get a bright spot, that is where you have maximum, and destructive is where you have minimum, where they cancel out. Okay, so the amplitudes cancel out, so it will be a dark spot. And this is what you have to know. So you have to know these letters and you have to know how to use this equation. So remember again, lambda is the wavelength of the waves, d is the slit to screen perpendicular distance, x is the fringe to fringe or bright fringe to bright fringe or dark fringe to dark fringe distance, center of one bright fringe to the center of the next bright fringe, not dark fringe. Okay, because some students confuse, they take it between two fringes. But if it's between two fringes, it can't be between bright and dark. It has to be either bright and bright or dark and dark. That is x. Then ax over d. So I already explained. So you have to remember this equation and you should be able to use it. So what is a, what is x, what is d, they are all given here. I already explained it. Now for consolidation, we can go through this example. In a double slit experiment using light from a helium neon laser, a student obtains the following results. Width of 10 fringes, now they haven't said whether it's dark or bright, 10x is equal to 1.5. Slit separation is 1.0 millimeters, slit to screen distance 2.40 meters. Determine the wavelength of the light. Work out the fringe separation. So first, now what we are supposed to find is the wavelength, lambda. So we can use this equation, lambda equals ax over d. A we know, d also we know, but the x only we have to first find. So x is, for 10 it is 1.5. So for 1 it will be, because this is the distance between 10 fringes. Okay, width of 10 fringes. So we want to find the width of one fringe. Width of one fringe is the same as the distance between one fringe to the next fringe, bright fringe to bright fringe. That is what. So it's 1.5 for 10. You divide by 10 and then you get this. So this will be x. Okay. So it's like from the middle, because we take it from the middle. So now imagine it's like this. So this is the middle of the dark fringe. So you can imagine from here to here dark, from here to here bright. So that's why if you get the distance between the fringes like that, that is x. Okay, then you can substitute and get the answer. Okay, this you can convert to nanometers. This is in meters SI unit, so it's 630 nanometers. And remember, this is from a laser. So if it's in the visible region, it should be between 400 and 700 nanometers. It's in that range. So that you will be able to see it, like monochromatic light, the red light from the laser. Okay, so here this is also very similar, but because this is not monochromatic, they are using this monochromatic filter, getting it like this, and then from here only the diffraction occurs at this slit. So here this is already diffracted, this is already diffracted, but where the two overlap is only where you have interference. Okay, then diffraction grating I already explained. Remember that equation is very important. The equation for the diffraction grating, n lambda equals d sine theta. You should be able to use it correctly. Okay, I already explained this. Now we'll go through the example there for consolidation. Yeah, I think I already explained this, right? Yeah, so it's a matter of then substituting and getting it. So you do these questions and do the past paper questions or questions in the drive, then you will have a better understanding. So we have sine theta equals n lambda equals d sine theta. Go through this part. Then the summary. Okay, so principle of superposition we went through. When waves pass through a slit, they may be diffracted so that they spread out into the space beyond. The diffraction effect is greatest when the wavelength of the waves is similar to the width of the gap. You have learned this in the O-level class also. Interference is the superposition of waves from two coherent sources. So this is very important, coherent sources. Superposition of waves from two coherent sources. So remember, it comes from two places like this. So this is one coherent and this is another. So this is one coherent source, but because we want interference, we have to send it through the gap. Or if you have two coherent sources like this, let's say one here, one, then you can get interference. It has to be coherent. Okay, so here is one coherent source, then you can say this is the other coherent source. Actually, this is the only source, but when it's coming from here, we can think of this as two separate sources coming from this slit, and then you get the interference pattern. Okay. Then interference is superposition of waves from two coherent sources. Two sources are coherent when they emit waves that have a constant phase difference. Now I told you this is very important. You have to know what is coherent. When two sources are coherent, they emit waves that have a constant phase difference. And I told you, you should know what is constant phase difference. Okay, they have the same frequency and it remains the same. This can only happen if the waves have the same frequency or wavelength. For constructive interference, the path difference is a whole number of wavelengths. So 0 lambda, it can be lagging by 1 wavelength, 2 wavelengths, 3 wavelengths. Okay, so lambda we use for wavelength. Remember, in the wave equation, V equals F lambda. Lambda is the wavelength of the waves. So one wave can be lagging behind the other by 1 wavelength, 2 wavelengths, or it can be going together. So if they are both going together, then one is not lagging behind the other. So the path difference is 0 lambda. Then so you will have n lambda, and n is a whole number for constructive interference. For destructive interference, the path difference is an odd number of half wavelengths. So remember, this number here is a whole number, so it's like 1.5, 2. So n can be 0. If it's 0, then half. If it's 1, 1.5, 2.5, like that. So one wave is 1.5, 2.5, 3.5 waves behind the other, or lagging behind the other. Okay, so here the phase difference is 180 degrees, because one whole wave is 360. Here it is 360 plus, because one whole means 360 plus 180. Okay, here it is 0 degrees. Here it is 360 degrees. Then 360 times 2, 720. It's like that. Path difference we give in terms of wavelength. Phase difference we give in terms of angle. When light passes through a double slit, it is diffracted, and an interference pattern of equally spaced light and dark fringes is observed. Remember the double slit, 2 slits are there. So diffraction occurs at both slits, and then on the other side you will get interference where the diffracted waves overlap. It is diffracted and pattern of equally spaced light and dark fringes. So this can be used to determine the wavelength of light using the equation. Remember Young's double slit experiment. We learned this equation, lambda equals AX over D, and I told you this is very important. This equation can be used for all waves, including sound and microwaves. A diffraction grating diffracts light as its many slits or lines. At its many slits or lines. Now I told you diffraction grating is like a comb. There was a picture also. It has many slits like this. So at each slit diffraction occurs, and on the other side you get interference. A diffraction grating diffracts light at its many slits or lines. The diffracted light interferes in the space beyond the grating. The equation for a diffraction grating is n lambda equals d sine theta. And I told you about each of these, so very important. If n is 1, then theta is the angle between n equals 0 and n equals 1. If like this. If n is 1, then this angle theta is between n equals 0 and n equals 1. If n is 2, if you substitute 2 for n in the equation, then the angle is between n equals 0 and n equals 2. So from here all the way to here, that is the angle. If n equals 3, then the angle is from n equals 0 to n equals 3. Okay, so that is theta n, and lambda is the wavelength of the waves. D is the grating spacing or slit separation. That is the distance between the centers of 2 slits here, or between 2 slits also, you can say simply. Okay, so that's the end of that chapter on superposition of waves. Now there are a lot of animations also that you can watch online. If you search superposition of waves, you can watch the animation, because then it will be easy for you to understand how this thing happens, because you have to see some animations so that you understand it better. For example, if you go online on YouTube or somewhere, you can type interference of water waves, you will see something like this, and then you will see along that line, for example, where you will see all the displacements are 0, the resultant is 0, so it will be like along a line. The water doesn't move up or down there, so it will be flat. You will see there are a lot of videos you can watch, and you can watch these videos of these also, and even this. Now they will show you how the next chapter is on stationary waves, so you can see a lot of videos, because for waves you have to see a lot of animations and videos, and there are plenty online that you can watch. university website, Colorado PHET, you can search. There are a lot of animations on that website also, and there are a lot of YouTube videos as well. You can search on YouTube, and because like I said before, for waves you have to see what is happening, you have to see the animation, you have to see how the wave is moving. You can see all these experiments are there if you search on YouTube or online. You can see all these experiments with the microwave probe. You can see where it is reading 0, where it is reading maximum, like this, and it will be easy for you to understand that way. Even these things you can see how it's done and all, but these are also very simple. This is the equation, very important. You can go through this, you can read this, because I explained it already. It will be easy for you to understand it. Okay, so that is the end of that chapter then. And like I said before, you have to answer all these questions in the brown boxes. Go through the theory, make sure you understand the theory, and you have to answer all these questions in the brown boxes and check your answers with the solutions of the book, because that is also a way of learning. Okay, you can get the solutions to these books online. There are some websites that have it for free, and also you can you have to check your work. Okay, if you then make sure you understand everything, and after that you can start on the drive questions that we have. The questions on the drive, you can answer those questions, and also the past paper topical questions that we have with the explanation. You can do that, and while you do that, you can also answer the end of chapter question. But first thing is you have to answer all the questions in these brown boxes, then the questions with the explanation solutions, and then the topical questions, and with that you can do this one, and that way you have that way you can cover everything in this topic. Okay, so that's the end of the chapter on superposition of waves.